Right, next thing is that this is called combinations of functions. In pre-calculus, called combination functions. Next operation is called composition. Anybody remember about the composition? These are called combination, adding, multiplying. If I give you two functions, f of x and g of x, maybe they are in this basic function. What we can do with it, with add and multiply and all that, combination, right? But there's this interesting notion, so composition, that it is not coming from numbers. These are really coming from numbers, right? If I have two numbers, you add and subtract, multiply. So we do the same thing with the functions, but what about this composition? What is that composition? So here's an example that reminds you of this unique operation that's only available for functions. What's time there? Okay. So let's see. Here's an example. So I'm writing down g of x first, 5x plus 4, and f of x later. This is x cubed. So let me write down in different color the composition. I give you two functions, and he is talking about something called composition. What is it? Okay. So I wrote down g of x first because we play with the g of x first. So here is the function, and I mean, it's about creating a new function. So how do you understand the function? Go back to the first class of this semester. What was my definition of function? Right, you're given a number, right? Given a number x, and you understood what to do with that number. Sometimes mathematically, sometimes just algorithmic, and there's no way to write down a formula and things like that. So, given an x, what are we going to do? X is there. Next thing we do is that we calculate this quantity u. This is an algorithm. Given x, what do we do? Algorithm. What is that? U is this is what we're going to do, 5x plus 4. Where did the 5x plus 4 come from? The first function, right? So you apply your input to the first function. That's what I just did. Make sense? In general, we can write down like this. U is a g of x if g of x is something else. Make sense? And one more step we do is that now I want you to look at u as a quantity, number. I give you a number x, u is a number, correct? We went through 5x plus 4. Then what are we going to do with that number? The next step is that play with that second function. Y is going to be u cubed. You see what I did from second step to second position to third step? I applied the second function. Apply g of x first and get the output, and apply the second function. This is called composition, and it is not equal to product or anything like that. All right? So here, quotient is a fundamentally different operation, like that. Okay? So u cubed. So that summarizes nicely about this algorithm. So let's write down. So we can just write it down into one expression. What is u here? U is 5x plus 4. Is that right? That's what u was, and raised to third power. So if you combine this process, it's just 5x plus 4 raised to third power. Make sense? Okay. So if you look at this function, 5x plus 4 raised to third power, and you look at it here, I compute the 5x plus 4 first, and then raise that to the third power. That looks like order of operation I nailed down, right? But that idea of order of operation is now have a fancy name. What is that? Composition. First thing you do is 5x plus 4. Next thing you do is raising that quantity to third power. It was analyzed like that. The order of operation written down and called composition. So thinking about order of operation is like a decomposing the given function into a simpler function. Does that make sense? So now, if I have a derivative of this individual step, is there a way to combine this one into a derivative of the first? That's how it goes. All right? All right. So what's next is the notation of this. This one is often called, so you can, in general, write down, okay, it's f of u. What is u? Is u is a g of x. So we can just put it down like this. Does the notation also make sense? U is replaced by g of x, so g of x appears within the f of x. So this is not a new notation, and the notation makes sense if you think about it a little bit. This is kind of bulky notation, and mathematicians come up with a new notation. All right, we're going to call that f parenthesis g, f of g of x, like this. It's a new notation. It's f, and there's this little circle there. It's not filled in circle. It's not the product. It's a little circle there in the g. That's the name of a function. You remember the difference between the function and the name of the function and f of x? You remember the difference between f and f of x? F represents the idea, the algorithm procedure. F of x is the value, right? Is number. So f circle g is the name of the compound name of the function. So it represents the algorithm. Now if you plug in x, then it becomes a number, right? And because of this notation, they usually put parentheses around it here and go outside. So if you plug in x equals a number there, that finally becomes a number. These are the notation. Okay? Composition to functions. I realize that this is actually introduced in algebra course, not pre-calculus. All right. What about that? Now we create this function that looks like a 5x to the plus 4 raised to the third power, and our question is that derivative. What is the derivative of this one? If that's the question, what would you do? You have to find, if you have to find the derivative of 5x plus 4, expand it out, and that's the one easiest way. Or you can group it to product of two things. Do you see that way of doing that? And right. That's not what I asked. What I asked is a product rule, and how do you, can you split it a product of two things? Right? 5x plus 4 times 5x plus 2 to the raised to the second power. Then product rule applies, right? And you can apply the product rule again to the second part and so on. Okay? So there is a way to do that. But if this is 33rd power, then you're a bit reluctant. This is a little too much. So now there's this chain rule kicks in on how to take care of that, right? So here's the idea. Derivative is about, started from the slope of the secant line, remember? Slope of the secant line, this is how much the x is increased. Then there's u is a function of x, correct? U is a function of x. So how much u is increased is a fine notion. U is a function of x. I change x a little bit from the base point A, then I can certainly think about how much u changed depending on delta x, right? Now it seems like y is a function of u, right? U changed a little bit, so you can think of how much the y changed depending on how much u changed if I describe y as a function of u. Is this, step-by-step increment idea make sense? Right? But altogether, you can certainly think about, actually y is completely controlled by x. So you can certainly think about, okay, how much does y change while how much x changed? That's why we want to compute. Y as a function of x, not y as a function of u. So this would be slope of what line? Slope of the secant line, right? There's no limit. Slope of the secant line. How much did the y change while x is changing there, right? So if we have a better control and intermediate step, maybe we will write this one down in terms of these intermediate quantities. So let's do that. What we know from that stage here, delta y, how much the y changed in terms of delta u, we can certainly calculate that easily maybe. So you insert it there. But there was no delta u before in here, right? If the delta u appeared, remember that trigonometric limit calculation? If there's nothing that you inserted there, you got to cancel out, right? So I'm going to put that delta u up there. But delta x was there. Do you see these two things are equal to each other? Not questioning too much of the why I inserted delta u. You understand these two things are equal to each other, right? Called multiplication by 1. Delta u divided by delta u. Make sense? All right, but let's think about the behavior in here. That seems like what behaves. Only the problem is that delta u is not independent. Delta u is dependent. Does this word make sense? Delta x is independent. We're going to control that, and especially we're going to control so that it is always non-zero number. Remember, delta x is not going to be 0. It's going to be awfully close to 0, right? But we don't have a control in delta u. When you're considering delta u divided by delta y divided by delta u, the delta u better not be 0. Is that right? But we don't have a control in delta u. Delta u might be 0. Who knows? Right? But delta x definitely not 0. So that's why it appeared in the denominator. So this one has a little problem, logical problem. What if the delta u is a 0? Goes into some tedious, boring procedure. So I'll skip it. They take care of it. Let's not worry about that. But that's something that must have come to your mind if you are logical at this stage. But let's ignore that. Let's look about the behavior. What's the behavior of this one as delta x approaches 0? But because of the continuity, delta u approaches 0, delta y approaches 0. So these are all indeterminate form. What is this Leibniz's notation? What happens to delta u divided by delta y divided by delta u? Not approaching 0 is indeterminate form. Leibniz invented this notation. What was it? dy du. Y as a function of u, that's going to be the derivative of y as a function of u. Right? What about the second part? U as a function of x. Makes perfect sense. U as a function of x, and that's going to be du dx. If they exist, right? And we assume everything here is differentiable and exists. Does that make sense? So that's supposed to approach dy dx as well, right? So we got the formula here. Dy dx, y as a function of x, derivative, according to this Leibniz's notation, is delta analysis, seems like dy divided by what? Not divided by, dy du. This is not divided by, it's compound symbol, times du dx. All right? That's what that is. All right. Isn't that kind of intuitive and easy to memorize? This du dx and dy du kind of cancel. Actually is what the cancellation happening in the delta level, not dy du level, right? Does that make sense? All right, let's calculate dy du. You see y as a function of u? Y is a function of u? What is it? Y is a function of u. What is dy du? 3u squared, isn't that right? Y as a function of u. Derivative with respect to u is a 3u squared. Correct? How about u as a function of x? Where is that formula? It's right there, u as a function of x. What is du dx? 5. Boom. The d is gone, right? All you have to do is write down. What was u? Go back to u. U is 5x plus 4. And second here, and 5 is outside. Correct? Looks almost like a proof, does it not? Except that the delta u being 0, that bugger, right? So other than that, it's almost like a proof. So we're not going to go into proof. You hang on to this idea just to understand the principle behind this this thing. So let's write it down. D dx. What was a function? 5x plus 4 raised to third power, right? We looked at this expression and then no direct derivative rules applied at this stage. Product rule, quotient rule, none of the basic thing. So you understood. I'm going to decompose it, right? Compose it and decompose it. First, you do 5x plus 4, and then we can differentiate it. What was the answer? 3 comes down, and 5x plus 4, and decrease it. Looks a lot like the usual derivative rule of x to the n, but you got to multiply something, right? What was that? The answer is 5, and I want you to think about, where did that 5 come from? Derivative of what? 5x plus 4. Can you put your head around and kind of understand in terms of action? Forget the whole thing. Seems like what he's doing is pulling out like that and subtracted 1, and he multiplied by something. Multiply by something. You have to focus on what did he multiply by. It's a derivative of 5x plus 4. Because 5x plus 4 is not x. If it's this x to the third, you will just 3 times x to the second. but it wasn't x. Then what he did is to multiply that thing that wasn't x. There's a quick way of doing it. Okay? So I allow you to do that. But if